In this episode of Exploring Data Science, we'll consider classification and regression via mathematical functions. In particular, we'll look at what exactly does it mean when we say a model fits the data well. For more in-depth reading around these topics, you can refer to Chapter 4 of the book Data Science for Business by Provost and Fawcett. Let's first consider classification via mathematical functions. Consider the raw data points on the graph shown. The two axes represent the attributes age and balance. The data points show two classes or decisions represented by a plus symbol or a dot. Can you spot any natural division between the two classes? We can indeed separate the instances almost perfectly by class if we're allowed to introduce a boundary that is a straight line, as shown. This is called a linear classifier and is essentially a weighted sum of the values for the various attributes. The line in the image can be expressed in this form, with balance in thousands, as age equals minus 1.5 times the balance plus 60. We would classify an instance x as a plus if it is above the line and as a dot if it is below the line. Here we have this expressed as a classification function. This is called a linear discriminant because it discriminates between the classes, and the function of the decision boundary is a linear combination, a weighted sum, of the attributes. In the 2 dimensions of our example, the linear combination corresponds to a line. In 3 dimensions, the decision boundary is a plane, and in higher dimensions, it is a hyperplane. For our purposes, the important thing is that we can express the model as a weighted sum of the attribute values. This linear model is a different sort of multivariate supervised segmentation, as has been discussed previously. Our goal with supervised segmentation still is to separate the data into regions with different values of the target variable. The difference is that the method for taking multiple attributes into account is to create a mathematical function of them. Let's now consider a slightly different dataset. Here we have a basic instance space in 2 dimensions containing points of 2 classes, as before. But how would we go about choosing the best line to separate the classes? How many different options are there? It's not a trivial task to choose the best line to separate the classes. In fact, as the image begins to demonstrate, there are, in fact, an infinite number of lines or models that classify this training set perfectly. So, which should we pick? One approach we can use is the support vector machine approach, or SVM. Support vector machines are linear discriminants in that they are based on a linear function of the features. How do SVMs work? Simply put, instead of thinking about separating with a line, we first fit the fattest bar between the classes. Once the widest or fattest bar is found, the linear discriminant will be the center line through the bar, the solid middle line shown in the image. Simple, yet elegant. At this point, let's make sure we understand the difference between classification and regression. Classification is the task of predicting a discrete class label. Regression is the task of predicting a continuous quantity. In some cases, it is possible to convert a regression problem to a classification problem. For example, amounts in a continuous range between 0 and 100 could be converted into 2 buckets, class 0, which would have the values of 0 to 49, and class 1, which might have the values 50 to 100. Linear regression, logistic regression, and support vector machines are all very similar instances of our basic fundamental technique, fitting a linear model to data. The key difference is that each uses a different objective function. Remember that for regression problems, the target variable is numeric. The linear function estimates this numeric target value using the equation shown. The training data have the actual target value. Therefore, we can think about the fit of the model as how far away are the estimated values from the true values on the training data? In other words, how big is the error of the fitted model? For a particular training dataset, we could compute this error for each individual data point and sum up the results. Then, the model that fits the data best would be the model with the minimum sum of errors on the training data. And that is exactly what regression procedures do. But how? The method that might seem most natural is to simply subtract one from the other and take the absolute value. So if I predict 10 and the actual value is 12 or 8, I make an error of 2. This is called absolute error. But this is not what standard linear regression procedures do. Standard linear regression procedures instead minimize the sum or mean of the squares of these errors, which gives the procedure its common name, least squares regression. Why is this so popular? Simply put, convenience. Originally, the least squared error function was introduced by the famous 18th century mathematician Carl Friedrich Gauss, and there are certain theoretical arguments for its use, relating to the normal or Gaussian distribution. Analysts often claim to prefer squared error because it strongly penalizes very large errors. Whether that penalty is actually appropriate is specific to each application. For example, why not take the fourth power of the errors and penalize large errors even more strongly? A serious drawback is that it's very sensitive to the data. Erroneous or otherwise outlying data points can severely skew the resultant linear function. For probability estimation, logistic regression uses the same linear model as do our linear discriminants for classification and linear regression for estimating numeric target values. The output of the logistic regression model is interpreted as the log odds of class membership. These log odds can be translated directly into the probability of class membership. Therefore, logistic regression often is thought of simply as a model for the probability of class membership. Without going too deep into the math, here is a visual example of how different approaches can lead to very different models. An apparent outlier is in this dataset of flowers, as highlighted by the red arrow. The logistic regression model is sensitive to this outlier and adjusts itself quite dramatically. The support vector machine model, on the other hand, remains almost unchanged. Without this outlier in the dataset, both the logistic regression and support vector machine models would look quite similar. To summarize, there are many varieties of function fitting techniques, but most use the same linear model structure, a simple weighted sum of the attribute values. The parameters to be fit by the data mining are the weights on the attributes. Linear modeling techniques include linear discriminants such as support vector machines, logistic regression, and traditional linear regression.